I am kind of excited about how this new PurpleHat track measuring sensor for the IoTT stick is performing. In this video I show you why. And if you watch to the end, you will see what additional features are still in the makings. Welcome to the IoTT channel. I am Hans Tanner. In the last video I showed you how to install the sensor magnets on the axle of N and HO scale cars. Today I am showing you how to install the sensor inside of the car, how to configure it and what data you can get. I am using an HO scale car to demonstrate, but it works exactly the same way for all the other scales. If you found the installation of the magnets easy and doable, then the installation of the sensor is a piece of cake. I made this PurpleHat PCB I quickly showed at the end of the last video, where the 3D Hall sensor is soldered on. It also has the solder pads for the IMU board, but on this prototype I installed pin headers so that I can easily swap the IMU board. To the left are the soldering pads for the IoTT hat connector, so the IoTT stick is simply connected to the hat then placed above the axle with the magnet, and the track measuring car is ready to go. Now, in the time since the last video, I have put some more efforts into board development, and this is how the next generation of the board is going to look like. The most important change is that it now has two sets of soldering pads for the Hall sensor. This allows to install the board vertically with the sensor still as close to the axle as possible. That way the board fits into an N-scale car and the IoTT stick display can be read through an opening in the sidewall of the car. But that I will show in a future video once I have the modified boards available. If you don't want to miss that, it is a good idea to subscribe to the IoTT channel and hit the bell icon so you will be notified when new videos come out. Once the sensor board is installed, you can switch on the IoTT stick, connect it to your Wi-Fi or configure it to act as access point as shown in video number 42. Then you can point your browser to the IoTT stick and load the node configuration page. On this page you first select PurpleHat as your function module. Then you select the communication interface according to your setup. With the PurpleHat you can currently use the options None, Loconet over MQTT or Loconet LB server client. Select None if you want to use the PurpleHat as a standalone measuring sensor without connection to a command control system. Loconet over MQTT can be used if you have a Loconet to MQTT gateway installed that sends the Loconet commands to an MQTT broker. The Loconet LB server client option lets you connect to any Loconet LB server, for example the LB server built into JMRI, or an advanced command station like the DigiKeys DR5000. Connecting the measuring car to a command station network is not necessary for basic operation, but it allows for some nice additional features I will show you in a minute. Once you have configured the IoTT stick to use PurpleHat, the web browser will display the PurpleHat tab. Click the tab and after opening the page, the first tab on that page covers the basic setup of the sensor. Here you can set the technical details to operate the device. The first and probably most important input is the wheel diameter. Measure the diameter of the wheel of the axle the magnets are mounted on and enter it in this field. The dimension is always metric, even if you configure the stick to display imperial dimensions. The best way to measure the data is using a calipers and measure the wheel directly. Since the running surface of the wheel is conical, the best place to measure it is about halfway between the start of the flange and the outer side of the wheel. Keep in mind that the wheel diameter is used to calculate the travel distance of the car, so setting a correct diameter is directly impacting the precision of the distance measurement. The second entry is for the magnetic threshold. Depending on the strength of the magnetic field, the measurements oscillate around the true value, even if the car is not moving. This oscillation would be interpreted by the software as constant small movements and change of direction. To avoid that, the threshold allows for specifying a rotation angle that needs to be surpassed before the sensor is interpreting it as a change of the travel direction of the car. So, the stronger the magnetic field, the less oscillation and the lower threshold value can be set. Very weak signals cause wider oscillation of the measured value, and therefore the threshold should be set to a higher value. Based on my tests so far, 15 might be a good starting point for most applications. But if the car is not moving, but then still continuously displaying changing speeds, you should try to increase the threshold value to make the sensor less responsive. This might be a good time to have a quick look into the software algorithm that performs the distance measurement. If you are not interested in that technical stuff, simply skip to the next section. The TMAC 5273 can do up to 1000 measurements per second, but it also offers the possibility to average the results of several measurements and read it out less frequently. I have set it to average the last 32 readings, which already eliminates a lot of the typical oscillation. In turn, the maximum sample rate is down to 400 readings per second, which is still more than what I do. The stick is configured to read the angle every 5 milliseconds, so 200 times per second. I then compare the new angle to the previous one and determine how much the wheel has turned. This is multiplied by the wheel diameter times pi, which gives me the travel distance, and divided by the time between two readings, the speed. So I get a new speed reading every 5 milliseconds, which then gets smoothened over half a second, which is then the result that is displayed. Now the interesting question is, how fast can the car travel and still provide an accurate measurement? Well, to reliably detect the speed and direction of the rotation, the angle between any two measurements must be less than 180 degrees. And with the typical reading errors, I think the measurement is reliable as long as I have 3 or more samples per revolution, which gives a minimum time of 15 milliseconds per axle revolution, or about 67 revolutions per second. With a typical wheel diameter of 11 mm in HO scale, this is equal to a speed of about 2300 mm per second, or converted to scale speed, about 725 km per hour or 450 miles per hour. So this should be enough even if you are modeling the German ICE railway system. And with that, back to the configuration screen. The reverse steer checkbox lets you change the travel direction the car interprets and displays as forward moving. You can use this to synchronize the indicated direction with the direction the locomotive is traveling. Of course, alternatively, you could simply turn the car 180 degrees for the same effect. It's up to you. On the second line, you have the drop-down boxes for scale and dimension. Select the scale of your application from the list. The information is used to calculate the scale speed based on the physical speed as measured by the sensor. So if you set this to HO, the physical speed as measured is multiplied by 87 and then converted to either kilometers per hour or miles per hour, depending on the selection you make from the dimension drop-down list in the next field. And that's all the settings you need to make to configure the sensor. Click Save and Restart to make the changes permanent, and you are ready to roll. If you now check the display on the stick and use the main button to rotate through the different pages, you get to a page that shows all the sensor measurements for speed, distance, heading, grade and super elevation. If you are using a regular stick C, that's it. In case you are using the newer stick C+, you will get an additional line that has the current rotation angle of the measured axle. This allows for very fine measurements of the movement, but it requires the larger display of the stick C+ with higher resolution. Another advantage of the stick C+ is the higher battery capacity. With the stick C+, you will be able to operate the sensor with activated Wi-Fi for about half an hour, while on the regular stick C you will only get about 15 minutes before it needs to be recharged. For this reason I have added a battery connector to the latest PCB version so that a small lithium-ion battery can be connected to the board. For my tests I was adding a 450 mAh 3.7 volt battery and got a runtime of about 6 hours, which should be sufficient for most applications. And finally, it is also to say that M5 Stack, the company who makes the stick C, has now completely switched to the Plus version and does no longer make the regular stick C. I have currently 2 or 3 left, and after that I will also only sell the stick C+. To see the results in the browser instead of on the stick display, open the Track Data tab. Here you first have 4 buttons to control the sensor data flow. The Start button is used to start and stop the data display in the browser. Note that the sensor keeps measuring in any case, and the current data is always displayed on the stick display. The Start button only controls the transfer of data to the browser display so that you can stop the flow to study the data in detail. The next 2 buttons allow you to reset the display on the fly. Reset Distance sets absolute and relative distance to 0. Reset Orientation, on the other hand, resets heading, grade and super elevation. Note that this is basically just setting the values for what the IMU considers north, flat and level based on the current position, so it impacts the display of heading, grade and super elevation. The final button lets you make a connection to the locomotive that is pulling the measuring car. Click the button, then issue a speed or function command from your throttle to the loco address and it gets paired with the PurpleHat via LocoNet if LocoNet is selected in the node configuration. If the sensor knows what loco address is used for the train, it can display the speed step that currently is set in the locomotive. That's what you see in the next 2 fields, the assigned DCC address and the current speed level of that address. The next section shows the speed and distance information. First, the physical speed as measured by the sensor. Note that this is always shown in millimeters per second, independent whether the display is set to metric or imperial. The next field shows the selected scale and the measured speed converted to scale speed. The last 2 fields show absolute and relative travel distance. Absolute distance is always counting upwards, while relative distance counts up or down depending on the travel direction. So if you move the car a certain distance, then reverse direction and drive it back, the relative distance will be 0, while the absolute distance is twice the amount of where the car was when you changed the direction. The next section shows curve radius and orientation of the car. If the car is traveling through curves of more than about 7 feet radius, the display shows straight. If the radius is smaller than that, it is displayed in this field. Heading shows the current travel direction, with 0 being the direction the car was in when the sensor started up or when the reset orientation button was clicked the last time. Grade shows the grade of the track, positive numbers if it is climbing and negative numbers if the car is moving downhill. And super elevation shows the banking, with positive numbers if the track is leaning to the right and negative numbers the other way around. Like the grade, these values are always related to the current travel direction. That is basically all the data the sensor can measure, and all there is in the lower half of the page is the graphical display of the same data, and you can use the checkboxes to select or unselect individual line graphs. The first box has physical speed, scale speed and speed step as measured during the last 120 seconds. The second block shows curve radius and heading, while grade and super elevation are shown in the third set of line graphs. Note that the second two blocks are only available if the sensor is equipped with an IMU. Without an IMU, the sensor can only measure and display speed and distance data. So let's see what we can get when we operate the sensor. For this test I am using the Red Hat command station prototype I introduced in video number 85, which makes the DCC++ Arduino software a Loconet command station. To control the locomotive, I am using a Digitrax DT400 throttle. The command station communication is configured to Loconet LB server, so it provides a physical Loconet for the throttle and Loconet over TCP. The PurpleHat sensor is configured as Loconet LB server client and connected to the server of the command station, so it receives all Loconet commands via Wi-Fi. First, I assign the locomotive address by clicking the Assign button and then turning the knob on the handheld throttle, and the address is assigned and displayed. The track is a simple oval using Bachmann EasyLine track. The curves are using 18-inch radius sections, and the straight parts consist of 3 track pieces of 9-inch each. So the nominal length of the track is about 167 inches or about 4 meters and 24 centimeters. I first do a distance measurement by pushing the car over 2 sections of straight track. The nominal distance is 18 inches, which is 457.2 millimeters. So I place the car with the bumper plates at the rail joint and reset the distance indicator. Then I push the car down the track and stop it exactly after 2 sections. 454.6 millimeters, that is a difference of 0.6%. I then repeated the test several times, always with similar results. Now, the smallest difference between theoretical and measured value is to be expected when traveling on a straight track, so this is the optimal case. As soon as the car travels through curves, the tolerances will increase as the wheels tend to slip once in a while, particularly on my bumpy test track. So let's try it out. I place the train on the track behind a locomotive and reset the distance counter of the sensor. Then I let the train do a complete loop and stop it at the very same location. Here is the result. 421 centimeters compared to a theoretical value of 424. That is pretty close. In fact, the deviation is about 0.7%. Now, if you get larger deviations than say 2% and it is systematically too low or too high, you may want to adjust the diameter of the wheel in the sensor setup. Increase the diameter to get a longer distance measurement and vice versa. Keep in mind that every millimeter you add to the wheel diameter adds 3.14 millimeters per revolution to the measured distance. Now let's look at speed measurement. Here is what I do. I let the train run 3 consecutive laps at constant speed and measure the time it takes. I use 3 lap runs to minimize the measuring errors at the beginning and the end of the run. Next, I calculate the technical speed and compare it to the speed that is displayed on the sensor. Of course, the measured speed is not constant. It is oscillating as the car pulls or pushes a little bit and sometimes jumps over rail joiners, causing the wheel to lose contact with the rail and slow down, and so on. So I watch the values and write down the highest and lowest and use the average of them to calculate the speed. This is not very precise as it does not really account for the speed losses in the curves, but at least it is an indicator. I repeated this test for different speed step settings, and here is a table of all the results. As you can see, the measured speed is consistently within a few % of the timed values, so that's pretty good as well. Only at the 100% setting, the deviation is growing a little more towards the lower side, which I think comes from the car losing contact to the rail more often at this high speed. Looking at the graphs, you see how the speed is related to the speed step the locomotive is running at. The graphs for physical speed and scale speed are on top of each other due to the scaling of the y-axis of the graph. At the top speed, we can see that negative spike, which I believe comes from the wheel losing contact with the rail. We can clearly see that the speed graph is much more dynamic at the highest speed, but then that is a scale speed of about 225 km an hour, so I don't worry too much about that. In the heading graph, you see the heading changing from 0 to 360 degrees as the locomotive goes around the track. If the curve is horizontal, the train is on the straight section. The slopes indicate that heading is changing, that is when the car travels through the curves. And you see how the time for a complete cycle gets shorter with higher speeds. The radius display shows a radius of around 440 mm for the times the car travels through the curves. This compares to a theoretical value of 441 mm for the 18-inch curve, so it is pretty close as well. Note that the radius is not displayed while the track is straight because it's infinite. But you typically see how the value comes from infinity to 440 mm and then disappears towards infinity again once the curve ended. When this happens, the curve display should be suppressed. That is an error in the software I need to correct. When fixed, you will no longer see the radius graph when the track is straight. The grade line in the last block is flat, as it should be, but the super elevation line shows some bouncing of the car. And at higher speeds, we see the increased dynamic that comes from the centrifugal force as the car goes through the radii. However, this data is not very reliable as I am still using the same IMU I used in video number 82, which most likely has a drift problem on the axis. But due to the ongoing chip supply crisis, I have not been able to get the replacement for a price I am willing to pay, and the problem has to wait for the moment. So that is the information you can get from the Track Data tab. Now, of course, you probably already figured it out. If you can precisely measure the speed a locomotive is traveling at, and you can relate it to the speed step the locomotive is set to by the command station, maybe it is then somehow possible to use this system to support speed matching of locomotives. Well, I guess that is true, and this is exactly the functionality we will find in the next tab, which is labeled Speed Magic, and I will tell you more about it in the next video, so stay tuned. For today, that's it. I hope this video was interesting for you and you are as excited as I am about the simplicity of the PurpleHat sensor board and the quality of the measurement data we get out of it. If so, please click the like button below to let me know. Doing so helps to promote this video and the IoTT channel in general, because as you know, YouTube likes the likes. Thanks for watching and see you in the next video.